Our last video was a bit calculation heavy, but the good news is there are absolutely no calculations in this video, just some kind of cool conceptual ideas. So enjoy. We're going to be looking at electric fields inside conductors. So if we imagine having a spherical shell of metal, so it's a conductor, and initially it's neutral, and then we put some charge inside. In this case it's a positive charge. Well, you're going to get an induced charge on the inner surface. It's going to be a negative charge because the electrons will be attracted to the positive charge, and you'll have the same amount of positive charge because this was initially neutral. So however much you moved away of negative charge, you have that same magnitude of positive charge on the outside. And so if you have negative and positive charge, essentially you're creating an electric field in the interior here that is going in the exact opposite direction from the electric field due to the charge. So you have your electric field from your charge and your electric field from the induced charge in the conductor, and those two things will cancel out. And so these types of effects give us some generalizations we can make, that the electric field inside a conductor, and by inside we mean in the material itself, not in the interior here, because we still have an electric field on the interior in the empty space here. But inside the actual material of the conductor, it is always zero. And we can also see that because if there were an electric field, a conductor means that the electrons are free to move. And if there's an electric field, that means there's a force on the charges, and so those charges would continue moving until there's no more force. And that means if there's no more force, there's no more electric field. So this has to be the case. It also so happens that if you have a net charge on a conductor, which isn't illustrated here, but say that this was initially charged, that net charge will always reside on the surface, on the outer surface. Essentially, that charge is going to try to spread itself out as far as possible. It's going to be repelled from the other charges. Okay, another piece of conceptual information for conductors. The electric field is always going to be perpendicular to the surface of a conductor. So here, if the field had a parallel component in addition to a perpendicular component, then the electrons could flow, there would be a force on them, and they would move. And they would keep moving once again until there was no force, which means there's no electric field, because as these charges move, they're changing the electric field, because the charges are what are creating the electric field to begin with. So this doesn't happen. You don't get parallel components to electric fields in conductors. You only have perpendicular components. So that is no good. You just have this guy right here. Now, these simple ideas have some interesting applications. One is known as a Faraday cage, or in general you could just call it electromagnetic shielding. And to look at this idea, let's say we have a box. We're only showing a cross section of it here, but say this is a complete metal box, hollow cube kind of thing, and we put it in between two charged plates. Well, those two charged plates are going to have an electric field between them that will be constant and uniform away from the edges, and we're going to get a similar thing that we saw with that charged hollow sphere, where this outside electric field, the external electric field, is going to cause the charges to move. The negative charges will move this way, leaving this side positively charged. So that external field is still there in a sense, but then this separation of charge on the interior is going to create an electric field in the opposite direction, and so it cancels out. And not only is the electric field zero inside the actual metal of this box, but if there's no sources of electric field, no charges in the cavity, you cannot have any electric field in the cavity either, because you're going to cancel out all the electric fields here. There's not going to be any electric fields in the middle here either. And so in a sense you can be safe inside of a metal enclosure from any electric fields. And radiation, electromagnetic radiation is associated with electric fields, so you're also safe from any types of electromagnetic signals or electrical discharges of any sort. So there's all kinds of technical applications of this where we shield different wires, or we shield sensitive electronics by putting them in metal boxes essentially. And there's a lot of really important applications, but there's also other crazy things we can do. If you happen to walk by a giant Tesla coil, which is what this thing is here, as long as you're in a metal cage, you are completely safe. There can be no electric field inside this cage, so the electrons can never jump through there. If you want to build a nice Faraday cage on the cheap in case you're being attacked by, I don't know, a Sith Lord or something, you just need a couple of shopping carts, and there you go, nice and safe. A few other examples. There's a lot of the conspiracy theorist paranoia crowd who likes Faraday cages. This guy built a mesh metal cage around his bed, and there can be holes in the metal as long as the holes are smaller than the wavelength of the signal that's trying to get in. It will block it. So he sleeps in a Faraday cage. This is a metal fabric here, so I don't know, I guess you're protecting your car in case of an EMP or something like that. I don't know. And there is the ever famous tinfoil hats. Now here you're not actually protected from beneath, but I guess this would give you some protection from signals from above trying to probe your brain. When I was looking for these pictures, I also found this interesting little gadget, which is kind of a metallic fabric, and this guy is advertising it as a way to block all wireless signals from reaching your phone. It is a little interesting. No signals can get in, but like we saw in that first slide where we had the charge inside the metal sphere, signals can actually get out. So if you're trying to hide from the CIA or something like this, and you just put your phone in this metallic case, well, you're not going to receive any calls, but you would still be sending signals out that they might be able to use to track you with or something like that. So I don't really see the point of this. Why don't you just turn your phone off? What's the point of having a non-working phone inside a Faraday cage, essentially? I tested this out, by the way. I took my phone and I wrapped it in aluminum foil, and then it would not receive any calls. And just to make sure that signals could get out, as the theory predicts, I connected a Bluetooth earpiece and then played some audio and wrapped my phone in the tin foil, and the Bluetooth still worked, which is also a wireless signal. So signals can go out, but not in. They do get obscured a little bit, but they can still pass through to some extent. And one other application, if you ever find yourself in an electric battle, well, a Faraday suit will protect you. Enjoy.